Okay, we're going to be picking up today with where we left off last week in probability. We discussed that probability of specific events, like the 3 coin flips, could be seen as a random process. Okay, I'm flipping the coin, I don't know what's going to happen. And once I flip them in whatever series or group I determine, I can choose to count the number of heads or the number of tails. Whatever I choose to measure and count becomes my random variable of this random process. Okay, so in class we worked extensively on a random process of flipping 3 coins and counted the random variable of the number of heads in each flip of 3. Okay. Once we did that, we looked at the individual probabilities of all of the possible outcomes, and we considered which outcomes would produce which random variables for us, and that helped us to think about that in terms of probability. Okay, we're just going to be expanding on that today. Okay, we're going to be going back and relying on a lot of those ideas that we looked at last week. So our difference with what we're going to add on to this week is that we are going to add a new classification for random variables. Okay. Remember we said a random variable could be a numeric result of any random process. Well, we're going to get a little more specific now. We're going to create a unique category of random variables, and these are called binomial random variables. Okay. Now, if we're dealing with a binomial situation, okay, and this has to come from the process. The process itself and its possible results are binomial, okay, not necessarily just the results. Okay, so let's think about what it takes to make a binomial situation. You perform a specific number n of trials, and n just is a letter we stand for any number. So it could be 100, could be 1,000, whatever. This n, we're saying there's a variable number of trials. So we know we're going to perform a specific number before we begin. Okay. Each trial has 2 outcomes, success or failure. Now, that doesn't mean it has to be literally the words success or failure. It just means that when we're looking at the outcome, we're looking for a situation where we're either going to be successful or not be successful. Okay, there's not going to be shades of gray or various answers we can choose there. The chance of success, which we call P here, is the same on each trial. Okay, so every time we perform an event or this random process, whatever we decided it was going to be, the probability of being successful based on whatever you defined as your success stays the same. So it can be 50% on the first trial and then 70% on the second. That won't work. Okay. The outcome of one trial does not affect the outcome of any other trial. Okay. So we have to have independence between these trials. Okay. Anytime we have some sort of scenario that satisfies those 4 conditions, we are in a binomial situation. Okay. So let's start out here with an example of what this would be. Okay. X is, whatever, that's our random variable, the number of successes in however many trials in a binomial scenario. Okay. In this case, X is not just a random variable, it's a specific kind of random variable, which is called binomial. And sometimes we can state it like this. Okay. The random variable here, we know we have a binomial situation, that's what this represents. N would be the number of trials, how many times we were going to do it. And then P would be the probability of success in each individual trial. Okay. So let's look at an example. If we define, just like we did in class last time, that X, a random variable that we're counting, is the number of heads in 3 flips of a fair coin, this is a binomial random variable. And why? Each flip is a trial. Okay, we're going to do that 3 times, so n equals 3. There are 2 outcomes for the trials, heads and tails. Since we're counting heads, that counts as a success for us. Just like we would think of it as a success if we were choosing if we have 1 out of 2 outcomes, heads is what we're counting, heads is our success, and the tails would be the failure. Probability of success is 0.5. It is the same every time we flip. That does not change. And the outcome of one flip does not affect the outcome of another. That's independence. So check, we've got all of the conditions met. Okay. Another example, you can make 70% of the free throw shots you attempt. Your shots don't affect each other. You go to the line and take 20 shots. Okay. If we have defined our random variable as y, we're going to count the number of shots you make out of this 20. Okay. So y is what we're counting, the number of shots I make. That's a binomial situation with 20 trials. I'm going to take 20 shots and a 70% chance of success, okay, because we're counting what attempts that you make. So 70% there, okay. Now let's try a non-example. What wouldn't work, okay? Let's say you have a family reunion with 25 people in attendance. Every person in attendance either does or does not have brown eyes. 60% of all people have brown eyes. Let Z, random variable, be the number of attendees with brown eyes. Okay. You might want to pause, wait just a second, and think about why would this not be binomial? Pause and think for a second. What reasons can you come up with that this scenario does not meet the conditions here that we have that say they must have to be binomial? Okay. So you may want to pause it just a second and then look at this page. Each person is a trial. That works out. Okay, we have 25 trials, so good to go. Success, we're counting brown eyes. So we've defined brown eyes as a success. Pretty much every other eye color would be a failure. Okay, so we have the success and fail condition. The probability of success, we had 60% people have brown eyes. We have another 60%. Okay, but where does the problem arise? It arises with this idea of independence. These children are not independent. It's a family reunion. So we have genetics in here, and genetics are playing a role in eye color. Okay, so we have killed the independence condition. So not a binomial situation. Okay, now once we are assured that we're working with a binomial situation, then we can move forward with how to attack these kind of ideas from a little bit of a different way than what we've been thinking. Okay, so let's think about this. You're taking a test. You have a multiple choice test with 20 questions. Each question has 4 choices, but only one is correct. You guess on every single question. And to pass, you must get at least 8 questions correct. What's the probability that you fail? Okay. Now, is this a binomial situation? That's the first thing we want to think of. Okay. We have a set number of trials. We're going to guess 20 times. Is the probability going to stay the same every single time? Each question has 4 choices, but only one is correct. So you have a 25% chance of being correct. You have a 75% chance of being wrong. Okay. You're going to guess on each question. So what does that mean? You are only relying on random chance. So that keeps the probability consistent among all the 20 questions. If there were any of these questions where you could eliminate a question or you knew a little bit about this, then you wouldn't have consistent probability here, okay? To pass, you have to get at least 8 correct, all right? So now why would we not definitely want to think about this necessarily by hand? Could we? I guess if we were really, really determined, we can draw a probability tree where we are talking about correct and incorrect for 20 different layers of a probability tree. I would probably not want to do that, okay? Because then we end up, with, ungodly amount of combinations that we can make here. And we would be looking for the only combinations that had at least 8 corrects. Okay, so if we want to know that specific probability, we're probably going to have to engage some software or some mathematical formula for us that's going to give us a shortcut to that sort of extended drawing and thinking. Okay. So we've already said we've got a 25% chance of getting it right. We're going to count the number of questions that are correct. We have a binomial situation here with 20 trials and a 25% chance of getting it correct. If you fail, that means you got at most 7. Okay, so we want the probability of failing. If we got 8, we would be correct. Okay, if we got 8, we would be passing. So the only way, if we're going to look at the probability of failure, we've got to count 7 and below. That's the only thing that works here. So we're looking for the probability that the number of questions we got correct is less than or equal to 7. Okay. We're introducing a new command in R, and it's called pBinomGC. Okay. If you're going to use pBinomGC, the first input focuses on the boundary of the range of successes. Okay. So in our case, that boundary was 7. Next comes the number of trials, then the probability of success in a single trial, and then more about our range of successes. The options we'll see today are below, between, and above, and these are determined by the type of inequality that we've established for the number of successes of interest. Okay, and lastly, we can ask R to produce a graph for us to show us this probability. Now, sometimes getting the binomial probability to include the numbers that you want it to include can be a little bit of a challenge for someone who's new to using R. Okay, being able to choose this number wisely, considering the inequality that we use, can sometimes present a problem. So here is my advice and instructions to you. Always, will this command work without the graph part? Sure, it will. But you should never make it without the graph, because once it graphs the probability that it's calculated for you, you want to use that graph to make sure that the solution you're seeing matches the inequality you were trying to represent. Okay, and you'll see that in just a second. Okay, so here's what we do. We input this command. R is going to generate this graphic for us, and it's going to tell us the area that it's shaded. Now, what does this represent? This is the column representing 7 correct, and these columns below would be 6, 5, 4, 3, 2, 1, 0, and above would be 8, 9, 10, and so forth. Okay, now do not expect to see a column, or at least a visibly vertical column, for every single possible number of questions, okay? Because if you're randomly guessing 20 questions in a row, it should start to make sense to you that once we get up near about half of the questions, then the probability for being able to randomly guess that is pretty much slim to none. Okay, if we're completely randomly guessing in 20 questions and only a 25% probability of getting them right, we should probably not expect to be scoring a 20 out of 20. Okay, so now why did I say have the graph on here? Because if you remember the inequality we wanted to use, it was the probability x was less than or equal to 7. Since my inequality said equal to 7, I want to be sure that in my graph, 7 is shaded. Okay? If it had just said less than 7, then I would want to be sure that 7 was not shaded and make sure it includes the proper bars. Now, this is a discrete scenario. You know, we're going to get 1, 2, 3, 4, 5. We're not getting 1.5, 2.5, and so forth. So that's why these bars are clearly defined. We have boundaries between these things. So right now, if you look at this and you look at the probability, it's saying you have about a 0.90 probability that you're going to get 7 or less. So it looks like you have about a 90% chance of failure in this case. Okay, that all the shaded area here represents the probability that this can go wrong. Okay. Note that when the event is of the less than or equal to, the endpoint number is the one entered in the command. Okay, so when we said less than or equal to right here in our inequality, you had that less than or equal to, then the boundary number that we put in was exactly the same one that was here in the inequality. Okay, let's look at another example. You toss a fair coin 100 times. What's the chance of getting between 45 and 55 heads, including 45 and 55? So my random variable is going to be the number of heads in a 100 flip. Okay. We want to know the probability that the number of heads is greater than or equal to 45, less than or equal to 55. We're going to use P binom GC again. Notice GC is capitalized. Now, look here at the boundary and the input. The difference was before input in R was a single number. That's because we were only comparing our number of questions correct to a single number. Here we are comparing our number of questions correct to two numbers. We want to be in between 45 and 55, but we also want to include 45 and 55. So whenever you want to include a range of values in R, you must essentially make a very small list, and that's what's going on here. Anytime we see the C occur before a set of parentheses, we know we're dealing with the list in R. So we've entered that in the lowest comma small or largest, close that in parentheses. We have a size of 100. Again, that represents the number of trials. Probability is 0.5. We're flipping a coin. So if we're thinking about getting heads, that's a 50% probability. And the region here is between, because essentially I want all of the possible outcomes starting at 45 and going all the way up to 55. Again, we want to see a graph, because when I see that graph, I want to know that 45 is included, 55 is included, and everything in between. Okay. We used a list whenever we are comparing to more than one number. Okay, now again, look at the graph that R should produce for you. Now, if you are not doing so, every time we introduce a new command into RStudio, you should immediately pause the video. You should open up your RStudio and you should attempt to type in that question yourself. Now, I know copying and pasting is efficient, but if you do not actually practice copying and pasting, you will find that you really struggle to use R when the command is not pre-typed for you, and that is going to lead to a lot of frustration. So please make sure you are stopping the videos, practicing typing it in yourself, and making sure you can produce the graphic that I have embedded in the slideshow. Okay. Now we wanted between 45 and 55, and we wanted to include both of those. So 45 is included, 55 is included, and then we have all of the responses in between. And we see that this is about 0.73 probability, or about 73% chance that we're going to get between 45 and 55 heads in 100 trials. Okay. So let's expand on that. What about the probability of getting less than 50? Okay, now we want P probability of the number of heads to be less than 50. Notice this does not have an equal to on it. So it's different from the first example. In order for this command to work correctly, we're going to have to adjust. Okay, now remember, we're counting in whole numbers. So if we want the probability of the number of heads to be less than 50, what's the highest number of heads in that group of trials we could get? 49, okay, can be less than or equal to 49 to satisfy that condition. So we're going to have to adjust and use that 49 in the binom command. Now, when does that work? Only when we do not have the equal to involved in the inequality. Okay, so we've got to adjust. If I want it to be less than 50, it cannot include 50 when it calculates the probability for these results. Okay, now I'm going to put this command in. Again, if you haven't been doing it, I would stop. I would pause the video right now and attempt to type in these commands into RStudio. You do not have to hit enter. Okay, you can keep typing straight across and see if you can produce the graph that's going to appear next. Okay, now this is the reason why I always encourage people to do the graph, to make it show you the graph, because it is not uncommon for someone to accidentally put 50 here when they should not have put 50. Now, how would they notice it? 50 would be shaded and included on the probability distribution. And we should know that that would not work, that I've not done something correct because I want less than 50. I do not want it to be included. Okay, so 46% chance or 0.46 probability that I will get less than 50 heads in 100 flips. Okay. Again, what about more, 54 or more heads? Okay, what's going to change now? This time we've got to adjust the region, just like last time, because we wanted less than. We used below. Here we're going to use above. Okay, 54 is included. Okay, 54 is included in the probability I'm looking for. So it's going to be my endpoint. I'm going to do this and let's see what happens. Okay, what happens here that's problematic for us? We see that it includes 55, but we said it was equal to 54, right? Could be equal to, so that something's not right. Okay, if you look closely, the first shaded bar, like we said, is 55. It's not 54. With an above and a greater than, okay, it is not the one that we would expect. Okay, above in RStudio treats this as a non-equal to. So we've got to adjust. Okay, again, that's why you always want to see this graph, because you want to know that whatever input you put in RStudio is going to include the probabilities that you actually want. And the graph is the easiest way to see that. There are some little hiccups in terms of how R interprets that. So, once you learn how to run the command, this is very simple. What you have to think about is after the graph is produced, does what's shaded match the probability that it's your intention to calculate? And that's something that you'll have to be careful about. In this case, when I look at it, I see 54 is included, everything above is shaded, and I see that that's a probability of 0.242, about a 24% chance of getting 54 or more heads. Okay, so a new scenario. When you roll a pair of dice 16 times, what's the probability that you roll a 6 or lower fewer than 5 times? That's part A, and then we'll look at part B. What's the chance you roll a 6 or lower at least 7 out of 16 tries? Okay, so let's start out with our conditions and sort of analyzing our situation first. We're going to let Z, or any random variable you choose, equal the number of times you roll a 6 or lower. Okay, so we're going to focus on A first. Getting a 6 or lower, that's a success for us. Okay, and we want the probability that it's going to happen less than 5. And then in B, we want the probability it's going to happen 7 or more times. Okay, now please make sure that you are comfortable with how the statements in the previous slide developed into these inequalities. Okay, so let's go back to A. Fewer than 5 times. Okay, what would that mean? It has to be less than 5. It could not be less than or equal to 5 because 5 is not fewer than 5. Same thing with part B. At least 7 out of 16 tries. At least 7 means 7 will work, but what else will work? Anything greater than 7. So please be sure that you are confident that you understand how those words translated to these inequalities. And also be thoughtful of the fact that this is something you have to pay very close attention to throughout homework and test questions, because it is very easy to make a mistake here that will cost you big time later on down the road. Okay, so let's try these answers when we get together. Okay, I am going to make a separate video for these. I'm going to have my in-class groups actually working these out in class. If you're not able to be in class, there will be a separate video that works through these, this practice scenario. Okay, so remember I told you in the last session that there was sort of a shortcut for finding the expected value rather than taking the probability of each one and multiplying that, adding those together, and so forth. Here we go. We're looking at expected value and standard deviation here. Now, in a binomial situation, this can work. Okay, in a binomial situation, we can take these little bit of a shortcuts to what we're looking for. So if we have a binomial situation with the distribution of a random variable, and we know the number of trials and the probability of success, then the expected value of whatever that random variable is going to be equal to the number of trials times the probability. And that should make sense, okay? If you're looking for the number of heads you expect to get in 100 trials, that should be an easy expected value because we have 100 trials and it's 50% chance to expect to get 50. We know we're probably not going to get exactly 50. It's possible we could, okay, but we may not. Standard deviation, square root of number of trials times probability, so same thing as here, times 1 minus the probability, so the complement. Complement times probability times the number of trials multiplied square root. Okay, so if we have, let's look at our example here. 100 trials, okay, we are counting, we expect 50% chance of heads, so we expect 50 heads. If we follow that example through with the standard deviation, 100 trials, 0.5 probability of a head, 1 minus 0.5 probability of a tail, okay, the failure. When we multiply all three of these things, take the square root, we get a 5. So when we flip a fair coin 100 times, you expect to get around 50 heads, give or take 5 for a chance variation, okay? So somewhere between 45 and 55 is what we expect to happen the majority of the time. In fact, about 2/3 of the time. Okay? So what are mean and standard deviation for Z, the number of times you roll the dice in fewer than 16 rolls of pair of dice? Okay, again, this will be in that separate video as well. So if it were me right now, I would pause my video, I would open up the slideshow, and I would go back to those individual questions, and I would attempt to do those on my own, and then I would compare that to the video.